Well, hello everybody, in person and on the call. My name is Colin Haws, and I have had the opportunity this past summer to work.
Push the button, please. Thank you.
To work with the hydrophone scanning tank. It's been quite an opportunity. So first, a little background on me. Going into my fourth year as a biomedical engineering student at UVA. In my free time this summer, I've been making my own hot sauce and playing a lot of disc golf. Makes me happy. Always been interested in medicine. Some of you may know I have celiac disease. And then more recently, I was looking through clinical trials for glioblastoma and found focus ultrasound and foundation. So that's pretty cool. And that brings us to present day. So today I'm talking about the hydrophone scanning tank, some of the optimization measures I've taken, as well as an application through 3D printed lenses. So some of you in the office may have passed by this glorified fish tank and wondered exactly what it does. Essentially, it is a 3-axis system marrying 2 softwares, one important in moving the motors and the other in signal analysis. It is our rendition of it, mostly for cost reasons. As you can see, with all parts, it costs less than $600 for us to make it, as opposed to the commercial system coming in around $80,000. So it includes 3D printed parts, some wiring, as well as our motors. It is worth noting Sam Clinard and Aaron have done a lot of the meat and potatoes in this project over the last 2 years. Very thankful for their efforts. What it actually does, if you put your transducer at the bottom of the tank and attach your hydrophone is a glorified microphone, you can measure your focal region, right, your treatment region of your individual transducer, which is quintessential in knowing exactly what volume you're able to treat as you move forward into those experiments, into those clinical trials. So as I said, we're hoping through our manuscript publication, which we're revising now, that this becomes adopted in Utah by Sam, as it has been. I think it's in Columbia, and then maybe Don takes it to Harvard. We'll wait and see. But the idea is that we want everyday scientists involved in focus ultrasound to have the opportunity to make their own system at a lower cost. Alrighty, so some of my first steps included a lot of rewiring and some coding to make sure that the user has accurate and precise control over the exact movements along the scanning tank. You see in this little video here, the motor stepping off of what's called a limit switch, which essentially, when you hit the switch, you're causing a change in voltage as read by our Arduino code. And this leads to a step off of the motor. This was a lot of the early beginnings of my project, just to make sure that when you step and hit this boundary, you're going to eventually go back to a hard home or a position that you can accurately know exactly where you are in the tank, which is important prior to each session so that you know you're in the right spot, because positioning in ultrasound obviously is very, very important. And then to test these changes, I did some resolution scans seen on the right. Pretty much it's a little 3D printed part with my webcam that's focused on a micro ruler, which is just a millimeter length scale, where we're measuring image displacement before and after a scan, which tells us exactly how accurate and resolved being it can distinguish 2 points at a certain distance. But we're comparing our system measurements to that of this commercial entity that we are trying to essentially create a replicate of. And after these tests, we see that our resolution is on par. It is similar to this commercial system, which is exciting. That means that we can use this for experiments for clinical use. All righty, and then this is our GUI, our graphical user interface. Spent a lot of time with this guy. This has all the buttons, the bells and whistles to make sure that when you do a scan, what's going to happen is under your control, and then what it outputs is also under your control. So kind of just moving clockwise, I put in algorithms to calculate a waveform generator with a signal to noise calculator, as well as a repositioning function. When the system inevitably crashes, you're able to reposition at the same point, as well as a full width half max calculator, which is essentially telling you how big your focal region is. A lot of this is just improving the user-friendly nature of our scanning tank so that when we push this off to clinicians, to other researchers, everyone's getting the same deliverables, both visually and quantitatively, so they can make those next steps. All right, so once we had that functionality updated and those specifications and our resolution ready to go, we thought, why not move it to another application? So we chose a lens project, and you might be thinking, why would you want to change the transducer and do this through a lens? So we have these 3D printed lenses, which have the ability to aim or enlarge your focal region, right, your treatment region with any transducer. And you might be seeing some of those fancy transcranial transducers where you can steer individual elements, thus having direct control over your focal region. For something such as our 350 kilohertz one element transducer, or any transducer really, introducing a lens has the ability to essentially contour your focal region. So that's what we're doing. We're making a bigger hotspot, a region of more homogeneous pressures, because we want, instead of an ablative temperature increase, we want our region to be more of a local hyperthermia. This is, of course, seen in enhancing drug efficacy, as well as in blood-brain barrier opening when paired with microbubbles. And of course, we want to be able to, flex a little bit of our Focal Ultrasound Foundation Hydrophone scanning tank by conducting all of our measurements with the lens in our own tank. Alrighty, so this kind of shows our iterative process that we went through in creating these lenses. We began by getting our speed of sound data, essentially putting a plastic plate in the way of our signal and tracking the arrival time before and after putting this plate. And we found what the speed of sound is in a tough resin material. Very exciting. And then we can input that into our thickness calculator program, which essentially is under the assumption that our signal is all going to make it to the focal region at the same time. So it adjusts incrementally along our lens, our thicknesses, such that that assumption holds true. That outputs some points, as you see in the top left of my little box here, which then you can import into Fusion, CAD that into a lens, print it with our fancy resin printer, and then you see it in practical use in our Focus Ultrasound scanning tank, and to visualize what our scanning region is looking like after applying this lens. So to kind of see some of these results in action, on the right is our scans, the top being our no lens scan, what we're used to seeing with our kind of concentric rings coming off of it. If you look at the 7.5 millimeter lens, this has the most promise for right now. Looking to the left, the 7.5 on our plot profile, right? Our plot profile just explains a line going through the maximum point. We see the 7.5 has these lobes on the side, these little hills, which is exactly what we're going for. Because for that homogeneity, for that pressure that's not too much, but it's going to be a larger region around our center focus, we want these lobes to be a little higher, a little bit more on the same acoustic pressure level. And so we're right now iterating between this 7.5 range with this inner radius, and then hoping to find attenuation values so that our initial signal point that's coming out of the very center of our focal region is not creating a single point ablation, but rather this hyperthermic environment that we're looking for. Alrighty, so this brings me to some of my big conclusions. The Hydrophone tank, after a little over 2 months with it, I can confidently say it's practical and a robust system for characterizing any of your transducers. Right now, we're in process of finishing some of those revisions so we can re-upload that manuscript, reach more of an audience, and of course, update the online documentation so that successors can have a good place, a good foundation. And then, of course, with the lens project, we're very excited about, early results. We're looking at more iterations and some simulations, testing exactly what our attenuation is looking like. But when I say iterable, the entire process from creating your points to your CAD design to your printing and your curation process, we're looking at can be done in a day. So this is something that can have practical use in personalizing towards transducers and personalizing towards patients. So we're very excited about the future directions. Wow, lots of people to thank, including Mr. Middleditch, Dr. Cassell, my advisors, Dr. Eames and Dr. Padilla, as well as my honorary advisors, Dr. Snell and Dave, and so many other people for making this a great experience. So thank you all. And if you have any questions, please let me know.
Hi, I put a question in the chat basically asking how much time does it take to scan one layer?
So if I heard correctly,
For 2D scan.
Yes.
for one layer, it depends on your resolution. Most of these images have been done at a 250 micron resolution. With that step size, we're looking at a scan taking about 20 minutes, which is a little bit longer than about 15 minutes for the commercial design. But a lot of that includes integrated pauses, which are required to acquire your signal in a safe and non-noisy method.
The reason I'm asking is because I've implemented such a system in the InsightTech body system, which is a built-in function that technicians are used in order to scan the well-being of the transducer. And there we finish a complete scan at 100 micron resolution in something like 5 minutes. And the trick for doing that is having sort of a gating mechanism so we don't stop the transducer motion ever. We just have a gate signal that let us capture in real time the hydrophone signal with almost, I would say, zero delay. But in any way, even if there is a delay, it's a constant delay that can be compensated for. So I don't know if you use that trick in that system, but feel free to borrow it, steal and implement.
Right. Yeah, that's an impressive measure there. A lot of this is done with a 20 millimeter by 20 millimeter scan, which kind of ranges outside of our focal region. And this has kind of been done with our lenses, especially because we're looking at those side lobes once you reach out of that focal region. But something like a low pass filter, or as you say, to continue the motion somehow, we might have to talk a little later about that, but that's pretty exciting.
Colin, are you doing any averaging of your signal, or?
The averaging is off of 16 acquisitions.
Okay, so in that case, if you're averaging 16 times, you wouldn't be able to use this exact method of a continuous motion. So that may be one confounding point. And I guess, Yoav, the other thing is that the most even plane for comparison would be to get a sense of how many acquisition points, I guess, how many points there are in your grid of measurements versus Colin's. Do you know offhand what that would be?
Yeah, it's one. It's one every tenth of a millimeter, and the field of view is like 50 millimeters by 50 millimeters. So it's larger than what you do. It's much faster. But anyway, and compared it, to the nominal scan, and the results are very accurate.
Well, we may have to talk with you more about that.
Something I'll look into. Thank you. Any other questions?